You know, there's this invisible boss running just about every piece of tech you own. Your computer, your phone, even your microwave, yep, that too. It's the operating system, and it's the fundamental software that manages everything. So today, we're going to take a tour of how this silent manager evolved from doing just one simple thing at a time to, well, juggling the countless tasks we throw at it every single day.
I mean, seriously, just think about what your computer is doing right now. You've probably got music streaming, maybe a dozen browser tabs open, and you're working on a document, all at the same time. How is that even possible? It totally feels like magic, right? But it's not. It's actually the result of this long, incredible history of really clever engineering. So let's unpack that story.
Okay, so to really get how we got here, we've got to go way back. Back to the very beginning, when computers were, well, a whole lot simpler. And their philosophy was strict. One task, one time.
And that brings us to our very first type, the Uni Programming Operating System. The name really gives it away, doesn't it? Uni meaning one. Only a single program, or what we call a process, could sit in the computer's main memory and run at any given moment. That's it.
And this diagram really shows you just how simple it was. You've got the operating system itself, and then one lonely process, labeled P1 here, taking up all the useful space in memory. No multitasking, no background downloads, nothing. Just one job from start to finish.
So what was the big problem with this? Well, it all boils down to one word: waste. A computer's brain, the CPU, is ridiculously fast. But if a program needed to do something slow, like wait for you to type something or read from a disk, that super fast CPU just had to sit there, twiddling its thumbs. It was a massive waste of power, and it was the very next big problem that just had to be solved.
And solving that exact problem led to the next giant leap in computing, the ability to juggle multiple processes at once. This, folks, this changed everything.
This chart here lays out the evolution perfectly. We go from having just one lonely process in memory to having a whole bunch of them, all ready to go. And the result? A huge jump in efficiency. Because now, while one program is doing something slow, waiting for the disk to spin up, the CPU can immediately switch over to another program and keep on working. No more waste of time.
And you can see the difference right here in this memory diagram. Instead of just that one process, the main memory is now packed with several, P1, P2, P3, and P4. The OS suddenly has this whole pool of jobs it can switch between to keep things humming.
Now, this brings up a really important concept, the degree of multiprogramming. It's just a fancy way of saying how many processes are loaded into memory at once. So the thinking was, hey, the more processes, the better, right? Well, yeah, but only up to a point.
This graph shows you that trade-off perfectly. See, as you add more processes, the CPU is kept busier and utilization goes up. That's the green part of the curve. Awesome. But there's a tipping point. If you add too many processes, the system just gets overwhelmed. It ends up spending all its time just switching between jobs, swapping them in and out of memory, instead of doing any actual work. Performance just falls off a cliff. That disastrous state is called thrashing, and the OS's whole goal is to live in that sweet spot right at the peak.
So how does the OS actually juggle all these processes? Well, there are two main strategies. In a non-preemptive system, a process basically says, I'll run until I'm done, thank you very much. But in a preemptive system, the OS is the boss. It can forcefully interrupt or preempt a running process to give another one a turn. And that preemption is absolutely crucial for making our systems feel responsive.
Right, so this whole idea of preemption and sharing the CPU, that leads us directly to the systems that feel way more personal and interactive. The kind we use every single day.
This brings us to the multitasking OS, also known as a time-sharing system. It takes multi-programming and kicks it up a notch by switching between processes incredibly fast. It often uses a round-robin method, where every process gets a tiny, tiny slice of CPU time before the OS zips to the next one. This happens so quickly that it creates this amazing illusion that everything is running at the exact same time. It's how you can listen to music while you're writing an email.
And if you take that a step further, you get the multi-user OS. This is pretty cool. It allows lots of different people to use the same powerful computer at the same time, each with their own separate desktop and files. It literally feels like everyone has their own private machine. This is huge for the big servers that power universities or companies. Linux and Unix are the classic examples here, while Windows, for the most part, is designed as a single-user system.
Okay, so up to now, we've been talking about making one CPU, one brain do more stuff.
But what happens when you start throwing more brains into the mix? How does the operating system handle more than one processor?
And that's exactly where the multiprocessing OS comes in. Its entire reason for being is to manage and utilize a system with multiple CPUs, or what we now call cores, to just dramatically boost computing power. Pretty much every modern computer and smartphone is a multiprocessing system.
Now, there are two main ways to build these multi-CPU systems. On the left, you've got a tightly coupled system, where all the CPUs share one big pool of memory. Think of it like a team of chefs all working in the same kitchen. On the right, you have a loosely coupled system, where each CPU has its own private memory. That's more like a bunch of chefs in their own separate kitchens passing ingredients back and forth. Each approach has its own strengths.
And all of this brings us to today, to the modern era, where operating systems have become incredibly specialized to power, well, just about every device you can possibly imagine.
First up, we have the embedded OS. These are the real unsung heroes of our digital world. They're designed for one specific task inside a device, like your car's navigation system or a smartwatch. They're built for pure reliability and function, not for browsing TikTok. Next is the Real-Time Operating System, or RTOS. Now, for these systems, getting the right answer isn't good enough. You have to get the right answer at the right time. Every single process has a strict deadline, and missing that deadline can mean total failure.
The stakes? Well, they could not be higher. Just imagine the OS that's used for launching a rocket. A command that executes even a fraction of a second too late could be, well, catastrophic. There are absolutely no do-overs.
Not all real-time systems are quite that intense, though. We can break them down into two types. You've got hard RTOs, like in our rocket example, where deadlines are absolute. Missing one is a critical failure. End of story. But then you have soft RTOs, which can tolerate some minor delays. Think about streaming a video. A dropped frame here and there is annoying, for sure, but it's not a catastrophe.
And finally, we land on the operating systems that are probably most familiar to all of us, the handheld OS. These are designed specifically for the unique challenges of small, battery-powered devices with touchscreens. And of course, the two giants in this space are Apple's iOS and Google's Android.
So there you have it. We've seen how operating systems have evolved from doing one thing at a time to managing our entire connected lives. And every single leap forward was driven by the need to solve a new, bigger problem. So that leaves us with one final thought. In a world of AI, quantum computing, and the Internet of Things, what are the problems that the next generation of operating systems will have to solve? What's going to be the next great leap for the invisible boss